I'm going to talk artificial general intelligence today. I will lightly touch on history, how's it been going, and I will cover ARC Prize 2024, which is the current big thing in AGI research. I'll start at 1997, when Deep Blue defeated Garry Kasparov in a chess match. Well, retrospectively looking, it's pretty simple, right? But back then, it was a huge deal, really. And various pundits who were covering after the chess match, they claimed that machines are now going to be rivaling humans in strategic thinking, and the Deep Blue exhibited traits of human-like intelligence, since chess back then was held as a triumph of human intelligence. So Garry Kasparov, well, he later claimed that it was as intelligent as an alarm clock. Well, and I think he was right. Kasparov, he was a little pissed, naturally, he just lost. But let me show you how Deep Blue worked. So, at its essence, it's a sophisticated tree search algorithm. So, you start the chess position, and then you take all possible moves. Then you generate all possible responses from your opponent, and you continue this process until you reach a certain depth. At this point, you would use a heuristic function to evaluate the final position, like, for example, what are the values of your pieces. And you would assign each position a score. Then you would apply sort of a minimax algorithm, which would go up the search tree while picking best moves for either you or your opponent. And you end up really with the score for every initial move you had, and you pick the best. That's it. Additionally, you could use some optimization techniques like Monte Carlo tree search or alpha beta pruning. That was the one used for Deep Blue. And that's basically to just eliminate some branches, which, from the search tree, which are unlikely to yield any good results. So just saving some precious computing resources. Is that human level intelligence, or is it an alarm clock? Well, the algorithm itself, it generalizes pretty well to other board games, where the search space really is not that large. But it really fails miserably at every other human endeavor. So, for example, average chess game, it would last like 40 moves. And chess engines can go up to 20 moves deep, in certain positions. And that's not enough to solve the full game of chess, but like plenty to beat an average or even best human chess player, right? Uh, but let's grab a random other computer game like Starcraft. So the humans can achieve 100 moves per minute. They call it actions per minute. And the game would last 20 minutes. So that would mean that you would be talking about 2,000 moves instead of 40. Plus the amount of possible moves every time, that would be much, much larger as well. So this algorithm really stands no chance. And what I think is most important is asking a question. So did we learn anything about human intelligence and the nature of it and how to create it by creating a chess machine which is capable of defeating Garry Kasparov? Not really. While Deep Blue's success, it was a huge technological milestone, it didn't bring us any closer to understanding or replicating human intelligence, in any broader sense, really. It just showcased a brute computational power and specific problem-solving ability, rather than the nuanced, flexible intelligence which humans possess. Fast forward to 2015, when humans developed good enough hardware to support deep neural networks. And they enabled us to tackle games much more complex than chess and with increasingly larger action space. Since now, instead of calculating on the fly, you can just train these deep neural networks on large data sets and hope that during the play itself, they would be able to generalize to previously unseen situations. One of the games is Go. which Google DeepMind managed to master with AlphaGo. Uh, AlphaStar followed to play the Starcraft, which I mentioned, while OpenAI tackled Dota 2. So since all of these games were played by deep neural networks, usually trained, both established data sets and some reinforcement learning, where these networks would get better while actually playing the game. And so they were able to locally generalize the situations, which, might not be encountered during the training phase. But really, that's where generalization stops. Dota 2, for example, has over 100 heroes, and only 16 were present during training phase. So does it mean that the program would be able to play a different set of heroes and maybe learn their skills while playing? Not at all, actually. You would have to go through the very expensive training phase again. And so the level of generalization, it's certainly above the alarm clock. It's still pretty meager. And you might even consider that any professional Dota 2 player would probably be able to play a similar game, like League of Legends, in a sufficiently high level. Well, again, that's totally out of question for the machine. I wanted to show you another game, a CoinRun. It's really a research paper where researchers tried to quantify a generalization speed in a game. So these would be procedurally generated levels, and the deep neural network we used was able to train on them and beat them pretty easily. But it failed very much to generalize to other levels, as you can see here. And it was only until it was shown thousands of levels, at which point it might be safe to assume that the game was really exhausted, meaning that any newly generated level, it would have already been seen in some similar shape before, right? So, given all that, while it was all very impressive, StarCraft and Dota 2, I followed that very much, what this generation of programs really showed us that no game is sacred, right? But a machine can acquire really impressive skills. It's still very much limited to a specific game. You might also remember AlphaZero, also a deep neural network, but it was supposedly game agnostic. So it would play various games, and one of them was chess. It was very good at it. But still, although it was a bit more generic, it still needed to be trained on that game. And once trained, it could only play that game. That's it. So, although it sounded promising at first, AlphaZero was pretty much had all the same limitations as others. It's time to talk about this seminal paper, which followed these new developments in 2019 on the measure of intelligence by Francois Chollet, who is the leading researcher in this field. The paper has it all, and it's a long, fascinating read. It goes very deep into this world of generalization, like defining types of generalization, degrees of it. It goes into formalizing everything and so on. But what I really read most clearly from it, that it's very important to distinguish local generalization, which is present in all previous examples I've given, as a known unknown, and versus broad, flexible generalization, which is tackling unknown unknowns, or basically an ability to acquire new skills on the fly. And to measure systems' ability to do that, the paper proposed ARC, Abstract and Reasoning Corpus, a sort of a puzzle, which is behind ARC Prize 2024. So ARC Prize 2024 is a competition which anyone can join via Kaggle, and you get $1 million if you get anywhere close to a regular human. That is solving 85% of the puzzles. There's a set of public puzzles which you can use to learn from, and then whatever program you produce, it would be evaluated against a hidden data set, hidden puzzles, right? So let's walk around some random puzzles. This one. So you're presented with a grid, basically input and output, example input and example output, and you get several examples, and you have to identify the pattern. Once you do that, you can solve the test puzzle like this, And that's the game, right? Why are these puzzles much harder than, say, chess or Dota 2? Well, the main reason that since the rules are so simple, just produce an output based on few examples, actual puzzles can be very different from one another. And you're forced to learn on the fly and see patterns and basically acquire a new skill every single time. And you can still attack this using a broad search algorithm like in chess, but it will be way harder. Neural networks, though, well, they're now encountering hundreds of different games which we haven't been trained on. Often, in this other example, uh, one example is not enough. If, for example, in this case, you see, you need more information, since this blue shape is encoding the color of this larger shape. And you need this, I think, yeah, you need this example to solve it. Some of them are easy, some are harder, but pretty much are solvable by humans with really no problems. And maximum grid size, like in this example, is 30 by 30, and there's 10 colors, as you can see. Uh, doesn't seem much, right? But you really have no way of guessing the answer, since there's only one right answer, and there's 10 to the 900 powered possible answers. Uh, just remind you that the number of atoms in the observable universe is 10 to the 80. So yeah, that's a huge number of possibilities. Important thing to note, I think, is the paper identifies some core knowledge priors, which as a human you would have naturally to have, to be able to solve these puzzles. So, for example, an objectness prior, right? Which would mean, like in this example, an ability to identify objects. In this case, we are separated by color, but maybe they could be the same color, but separated by space. So these are objects. You recognize them as objects. Uh, also an ability to understand the directions, do some basic geometry, do some counting, and so on. It's really a fun exercise, and you can, if you have an inkling to prove yourself, in case ChatGPT took your job, you can do this. So 2024 ARC prize competition, that's current, but it was already held 3 times, I think, 2020, 2022, and 2023. So what happened up to this point? So 2020 ARC prize was also held in Kaggle, and you can see the leaderboard here. IceCuber won. Congrats to him. So you might think that all these top 10 solutions are a step further to general intelligence, since we are really tackling a much harder problem, right? Well, no, no, not at all. Pretty much all of these posted solutions do something similar. I will show you IceCuber's one, since he won. So what he did, he defined sort of a domain-specific language, which really means that there's a set of 142 transformations, completely arbitrary number, for the input. And he applies up to 4 of them. So that means you can pretty much brute force that, right? You would need 102 to power of 4, sort of 400 million possible combinations. That's not too huge. And then you end up, when you try them all, and you end up with a one which would match the example output, you could apply just the same transformations on the test input, and that's good. Submit it. And if you don't find any, maybe you move to the next one. So then, of course, there's plenty of optimizations, and you can form a graph to exclude duplicates, for example, and so on. There's plenty of them. I won't go deep into that. But still, optimizations aside, it's still a brute force algorithm. And it kind of brings us a step back to Deep Blue, an alarm clock. So there were deep neural networks thrown at this problem, but we did not really come anywhere close to the top. A similar story likely repeated on 2022, since IceCuber won again. 2023, on the other hand, well, that's interesting, since, of course, large language models and transformer architecture became mainstream. And lo and behold, first prize, well, at least shared, it was won by a solution powered by a large language model, which is huge. LLM itself, it was fine-tuned on a larger synthetic data set. So since we have seen in 2020 competition, you can apply a bunch of transformations and really come up with a big data set, right? For neural network to train on. And you can then just use it to fine-tune it. There's also another thing he did called active inference, which means that some fine-tuning was done live against the test dataset. It's amazing, really. It turns out like large language models can fine-tune on really tiny amounts of data. So that helped, and there's various other techniques involved. But essentially, yeah, we had LLM beat the ARC prize. What does that mean? Well, it means that 2024 is going to be crazy, right? Since there's more and more LLMs, and they're going to be thrown at this problem, right? So the competition hosted on Kaggle, it's a bit constrained, right? There's no internet access allowed, meaning you cannot use any closed models, like GPT-4o, Claude, or Gemini. But there's also a secondary leaderboard, this one, which allows these models, right? And of course, they are evaluated on a public data set, test set. It's not private, since the private set is not available to these models. They cannot be submitted and they cannot access internet, right? One of our approaches, it recently claimed 50% on public test set. Previously, best solutions, by the way, were in the range of 20 to 30%, right? And of course, these were done on a private test set, which is different from public test set. So we cannot directly compare, but it's still huge. 50% is still huge. So the approach, that's truly fascinating. What we did here is we asked GPT-4o to generate a huge number, 5,000, right, of Python programs, which would execute the transformation from example input to example output. Then you would pick a small number of them and you would try to improve those. Again, same process. You ask the same GPT-4o and you ask them to improve on its own programs. And that's basically known as few-shot prompting, right? Finally, you come up with a winner program, which you use to process the test input, right? And you submit it. There's also other prompt engineering tricks involved, and it's really amazing. I don't know about you, but I'm also kind of getting the vibe that we are back to brute force search problem again, since, the amount of programs to generate at the searches is quite big, and we're just doing that with better tools. But yeah, we are getting closer to 85%. Keep in mind, since this is GPT-4o, it has not been fine-tuned. So if folks at OpenAI, for example, would grab GPT-4o and fine-tune it, well, they would likely achieve way better score. So there's also many other different LLMs. For example, baseline vanilla Claude 3.5 is already outperforming GPT-4o for some reason, so there's lots of that to explore. Of course, I have to repeat, none of them can be submitted for these competitions, but still we're achieving huge results. But also, and I think this is very important, one other thing which this article claimed, that the one which we achieved 50%, was that LLM's vision is terrible on grids. Because LLMs, they don't naturally have vision. And it's almost the same as, scoring people on how well we are able to take square roots of arbitrary numbers, right? And I think it's very important to note, because I think people are actually amazing in understanding two-dimensional abstractions. That is in our DNA. And we evolved on mapping, in two-dimensional spaces while hunting and gathering. We recognize faces and so on. We deal a lot with two-dimensional abstractions. Uh, Actually, three-dimensional worlds itself we live in, that's projected into our retinas, which are 2D. The brain then reconstructs the three-dimensional world for us, but the input itself of the world, that's 2D. So it's easiest for us to form 2D abstractions, even given, we do live in a three-dimensional world. And we keep many of our abstract concepts very much two-dimensional. So if we want to compare large language models to humans, ArcPrice is really not a fair game for large language models. I feel it would be way better to have these problems represented in a language text-based format. All that aside, ARC Prize 2024 is going to be amazing. I'm going to try it myself. Of a lack of resources, I'll probably keep to ARC 1D instead. That one's surprisingly not that trivial, and there's no need to throw a bunch of compute at it. So, fun times ahead. That's it for today. Thank you for watching.